2023, March 28, afternoon. Well, over the past 10 or so hours of reading from Maugin's nonlinear electromechanical effects and applications, what we've seen so far is that on the one hand, the text is very much condensed, and at the same time, much of what he presents as the explicatory is key in the definitions of what follow as derivations. Then that most of then what I read into it is a comment, and of course any errors are mine. There's not to be deemed any fault on the author's part if I've read things the wrong way or not. But at the same time, what it reflects is that there's quite a bit of thinking and background and context and knowledge that are the preliminaries, that are the prerequisites, that are required to have enough of a context, A, to carry out the linear curriculum and follow the linear narrative, and as well, B, understand the greater or wider context and as to why what's presented as the linear narrative and curriculum is in this larger, from its local to its global setting, its context, where everything in the universe is defined by the thing, and then what it's not, its context. And thus the context of a thing can basically be defined as everything that it is not. And that it's possible to define what are the affirmative and negative then, and these ideas of the Comenius language and a theory of everything, that there could result a theory of everything. And with regards to then some of the discussion in this readings has been about what are the settings of the entirety, what result that we can talk about a theory of potentials, or a theory of some potential, T sigma P, in terms of potential theory, which is the analysis of these harmonic functions in the setting where energy travels in the courses of being waves. In the course of that, in a unified field theory, what we have as the nonlinearity is after the classical and the linear. What are so results then for our fields of mathematics, of geometry and algebra and arithmetic, and the operator calculus in the tensorial settings, as of about the establishment of the mathematical model of what are our physical models of our science, that with regards to the scientific method, then from these fundamental theoretical first principles, it's so possible for us to arrive at what is a well understood entirety, thus that as we get into the reading of some more of Maugin's or Maugin's, as the case may be, a nonlinear electromechanical effects and applications, that it is possible to see that what would otherwise be an inscrutable sort of work can reflect, because it's a rather good work, that from a reading of it and enough of the context surrounding it, that it's possible to arrive at quite a good foothold in these learning mountains, that as we grade the learning curve and we reach past these learning hills and see beyond us these great vistas of the learning mountains about us, that it's possible to garner from instruction and in some sense experience what would help what would otherwise be for the autodidact's course and that of the needful, that we can arrive at quite a bit of condensed and open-ended knowledge as from these readings that overall encompass the course of a few days. So let us take a look here at nonlinear electromechanical effects and applications. Where we left off in the beginning of chapter 4, the first couple of pages, we had reached where we talked about that the waves are generated by two transducers in this convolver, where the crystalline substrate is nonlinear, emphasis to authors, elastic, emphasis to authors, vis-a-vis that it's not linear elastic, and that it's not linear inelastic, and it's not nonlinear inelastic, it's nonlinear elastic. where elasticity and inelasticity reflect for our classical kinematics what are the things that go into where there is deformation and lack thereof. And here, that with regards to the nonlinear, that it is having the nonlinear responses of the recitative and osculating and the dissipative and attenuating, that it so results we can frame the general contents of the aggregate media as having properties given particular dimensions and directions. The resulting potential distribution at each point x sub 1 in the interaction zone. This was described as the interaction zone in terms of waves and their constructive and destructive interference. We'll have the form v velocity of t, time, equals e sub 1. The energy is input times quantity t minus x1 over v naught, thus that it's reciprocal in v naught and proportional to x1, times e2 of t minus l naught minus x1 over v naught. Similarly, as of diminishing in x1 given l naught and reciprocal to v naught, the initial velocity, times the exponent of quantity imaginary I, quantity omega 1 plus omega 2 t, the wavelengths, and then the k1 minus k2 x1, the wave numbers. This can be recorded by a third interdigitated transducer, t underscore 3, from the diagram 4.1, that's being the section in the middle there, t underscore 3, between t1 and t2, the transducers, that is interdigitated or forked as of the comb that we discussed in the earlier reading, with spatial period 2 pi over quantity k1 minus k2. And this reflects that 2 pi is 2 pi radians, and 2 pi is the full period of revolution or period of a periodicity of a wave in its modular and clock, that 2 pi over the quantity k1 minus k2, the wave numbers, first digits, placed in the interaction zone. So in this case, when we say recorded, it's with regards to the sampling, measurement, and observer effects of a detector. That recording is not just the interaction, but also the detail of the output. If we now select omega 1 equals omega 2 equals omega, and thus k1 equals k2 equals k, the response of the device becomes spatially uniform along x underscore 1, and it can be detected by a continuous metallization. Continuous emphasized by the author, meaning without gaps, as complete, satisfying these continuity laws as what reflect the conservation laws. Metallization is that a metal has particular properties of how electricity is conducted through it, or that it conducts electricity. In terms of that, a metallization reflects a particular area of small electrical resistance vis-a-vis an insulator, which has effectively infinite electrical resistance, placed in the interaction zone instead of an interdigitated transducer. We obtain a so-called degenerate acoustic convolver. Degenerate, again, reflecting that it's as of a sort of thing, but it's as fallen into or broken into what under its first principles or what is as it is elementary, that it still maintains some property of being an elementary or fundamental thing, but that it is only basically half of that, degenerate, whereas then anything above that is defined as without adjective and just regular. Acoustic convolver. Then the detected component is obtained by integrating the relation 4.2, where 4.2 was defined this velocity, so is integrating this to define that the integral of velocity is often called acceleration, or rather the derivative is called the acceleration of velocity integrated results the passage, where that's a key and critical thing in this notion of the nonlinear in the global, is that velocity with regards to Newton's first and second laws, and object stays in motion, object stays at rest, that then this idea that the acceleration is all those higher order derivatives of the position function, and that velocity is the first derivative of, or change with respect to time of position, that as well, that is so modeled that all the accelerations are higher order from a higher order abstract infinite impulse back down to the unity again and back down to zero, where we reflect that classical motion results to classical rest in the middle, and whether or not anything can really truly be said to be at rest or to be at motion. And that is a usual sense of objectivity with regards to that. Of course, first we need to learn all the linear and classical before it can really start to make sense, all this holistic and as of about the monism of the universals. Then the detected component is obtained by integrating the relation 4.2, the velocity, between negative L naught over 2 and L plus L naught over 2, that being the length of the T3, the space that is the interdigitated transducer, or the one that is a continuous metallization with regards to, then it just has basically a configuration space as of passage of either a vacuum where it's free to travel in a vacuum, or as with regards in our model that it's kind of like a superfluid surface, or as where it's it just reflects that the wave will propagate without otherwise interaction or effect. Then the detected component is obtained by integrating the relation 4.2 between the left and right hand sides, and where the length is L naught and is defined in terms of this box in terms of the wavelength. Thus, given the input of the wave and given the input of the wavelength and the wave numbers, that these reflect what would be the points where there are minimum and maximum of the waves in terms of various of their properties. There as what would be orbits around them about the apogee and perigee, if you consider orbits around all the waves. That it is so that these particular parameters keep constant and fixed what would otherwise result that such additive results that result in cancelization and thus arithmetic and algebraic tractability would not hold so. From which there results Vt equals V naught exponent 2I imaginary omega t, and that's a usual notion of writing our period of rotation or period of oscillation of the regular motion of regular cyclical motion in a complex form with regard to that is so tractable for the differential analysis of the form of making integrals and derivatives about them. Integrating the integration bar of Leibniz, it's the script S, it's the integral bar. It reflects S that was originally sigma, where sigma is the summation of a finite or infinite series, that the S integral bar reflects a sum of these notions of usually the Riemann areas or regions in Leibniz's notation and our modern formalizations in the standard real analysis from T minus L naught over T 2V naught to T plus L naught over 2V naught. That L naught and V naught have, in terms of that formula, that preserves system of units, so that time and this notions of length and length per time and that result that any arithmetic and algebraic quantities that do happen to have the same units can be added and subtracted while maintaining those units. That it's those dimensions in those configuration spaces that so result that they have that they're of a like type and that they so relate. The integral with those bounds, the definite integral so evaluated for then that being in d tau, that being the region as described earlier with regards to why tau is written for t, that e underscore 1 tau plus e times e2 to t minus tau minus L naught over V naught. That being the quantity of the integrand, so that it results that where we have set tau equals t minus x1 over V naught. And this is where a substitution of variables is often a usual course, and we even have as well a transformation of coordinates. And these types of things where it's possible here that he's also parameterized it or defined the implicit that has to go into it, or the self-parameterization, or what would be called the reformulated, that this notion of substituting the variable explains why that the terms basically t naught plus minus the x1 over v naught results that this L naught and the length and this x1 the position at the given time through those lengths results that it's in a region in the middle, so that then we can talk about integrating and computing its area or volume respectively, integrating it, resulting in quantity in a higher dimension from a lower dimension. The parameters that, in given time, the other dimension, that it's so read here how Maugin has so defined this formula. Therefore, the amplitude of the detected signal with frequency 2 omega, it's its frequency in its wavelength, is its reciprocal, has for envelop the convolution product. Emphasis the authors that convolution is an operation, and in that its product is in the product space of convolutions of the two excitation signals E1 and E2. These are the stimulus, these are the inputs as what drive what results a wave from what is some linear input. E1 and E2 compressed in time by a factor 2. Guess what, when we read compressed in time, then that would be in terms of the signals and their time, as it were, that compressing it in time by a factor 2 reflects that then it results that what's otherwise worked up about the symmetry is 1 either side, and that 2 is again with reflecting that there's the unit interval 0, 1, there's the positive and negative unit interval from -1 to 1, it has length 2, and then with regards to the quadratic and solutions about the trigonometric and all these things that go into triangle law, Cauchy-Schwarz inequality, triangle inequality, and these kinds of things that result how we can write these terms symbolically in what also have representations as infinite series and their products normalized into this unit range, so that it's the higher order products of these terms are well defined and fall in the same range. In fact, the interaction time between E1 and E2 can be made very small as compared to the time of propagation along the central electrode. Electrode is basically anything that is an interface for the effect of electrons to affect passage. It's the trace, it's the pin, and in terms of positive, negative, and I forget which is which, the cathode and anode, the electrode, so that up to the offset term L naught minus V naught, where an offset reflects kind of like a coefficient, it reflects a linear variable as a scalar, that an offset is simply that which is a displacement with respect to otherwise an origin. L naught over V naught, for the amplitude of the signal, we can write S amplitude T equals V naught, the integral from negative infinity to infinity, or the integral as over the entire domain, real numbers. In here, d tau, as was mentioned, transformation of coordinates, transformation of variable in t, and as with regards to that it's parameterized, it's implicit about x1 over v naught, that the integral of e1 tau e2 to t minus tau dt times v naught, where v naught is an initial condition, results to amplitude. This was first used by the Soviet scientist A.A. Chaban, C-H-A-B-A-N, Chaban. Soviet Physics Solid State 9, 1968. This is where solid state reflects a device with no moving mechanical parts, and then how things work in them in terms of electrical and magnetic fields and anything else that doesn't involve moving parts, the kinetic or chemistry or radioactivity. Solid state, analog solid state, or digital. The most important factor to increase the power of nonlinear interaction needed in the convolver is the energy density. This is about the configuration of experiment, the energy of experiment, and the regimes of when things are linear and when things are nonlinear. The latter is much increased if one uses a so-called waveguide convolver. This is where the waveguide convolver basically provides an amplification of certain parts or aspects of what would be the ringing, or what is in terms of hysteresis, how it would be controlled, or how it would be let out and amplified, in terms of what are usual notions in signal analysis of a signal that is a periodic function of a wave in one dimension. That would be called an oscillation. That if one uses a so-called waveguide convolver, and he refers to P. Deffernaud and C. Mersfeld acoustic convolver using multi-strip beam width compressors. And there's some discussion to be made of beam width here. That's an interesting, unusual term, beam width. And as with respect to bandwidth, which is essentially a description of what information is possible in a signal to be carried in a wave of a certain amount of frequency range, and usually the radio waves, and as that various sections of bandwidth basically bracket that out to bands, and then these bands have widths. That the bandwidth is basically quantity, where old UHF television channels have like a 6 megahertz bandwidth, or along the lines of that various modern technologies have what's called packet radio, or how things are made digital and go over radio waves. And so Deffernaud and Mersfeld wrote about the multi-strip beam width compressors in IEEE, that's the International Electricians, Engineers, Ultrasonics Symposium Proceedings, 1974, of which the working principle is sketched out in Figure 4.3. Working principle of the waveguide convolver substrate is, e.g., lithium niobiate, LiNB03. Compressing elements are induced, C1 and C2, these being labels for these components in their diagram in the system, which provide very high energy densities on a width W of a few wavelengths. Compressing is thus defined as providing a very high energy density on a width, and is similar with compression in the digital information sense, that there's what's called Huffman encoding or entropy encoding, where Huffman encoding is named after a fellow named Huffman, who invented the very particular usual idea that the most occurring code gets the shortest code, and the least occurring code gets the longest code, thus that in the course of sending and receiving all the codes, that a given particular code or letter of the alphabet is received as of the least number of bits for the most commonly occurring code, and the and so on down the alphabet, and the histogram or table of counts of these codes that is possible to design for a given alphabet an optimal entropy encoding, and that's attributed to a guy named Huffman. And then there's also what's called arithmetic entropy encoding, and these other kinds of fields that are how JPEG images work, and how Lempel-Z-Welch encoding works, which is called gzip or deflate, and how the internet works in terms of that it sends huge amounts of data over a limited bandwidth by compressing data with loss and lossless compression techniques, would result that it arrives the feet of cats. Here he's describing in terms of an electrical sense that this energy density is basically as insofar as that there's that much more hysteresis in the wave. The waves are then guided by a central electrode of length L0, and the recording of the convolution signal is made in comparison with the short-circuited electrodes placed on both sides. So here he's establishing that you need a reference to make any measurement. And so we often think of this abstractly and objectively, is that there's an origin and everything's framed in terms of the origin. And here he's just describing that in this apparatus, that this system has it so that these other electrodes have, with regard to them being a trace or a pin or something that can be tapped and a passage across it measured, or device that's a detector, that these are like so, and so you can measure them in terms of each other. that it's subjective, and that's objective. It is a theoretical study of this type of convolver, which is given in the following sections. And then there's the diagram that we saw of the working principle of the waveguide convolver, and that these are the left and right electrodes that were mentioned, and this is the center one, and so it's kind of written with regard to that being the usual symbol for electrical ground. We have these two inputs and this output with regards to these interactions carry like so, and these compressors, they look kind of like amplifiers, or that when we start to look at symbols of electrical circuits in diagram, there are a lot of usual symbols that reflect what are active and passive components according to Ohm and Kirchhoff, according to Maxwell at least, that have then, when we think of it in terms of the amplifiers, and I'll have to think back to a little bit more of my theory of electrical circuits, that these what are called compressing elements may as well be regarded that they're just wrappings of wires, that they result that there's all sorts of usual elements in an electrical circuit that can be so defined. Then in the digital circuits, it's kind of similar. They have what's called standard logic. And standard logic is just arrays of gates that result digital signals in, digital signals out, and that they implement machines, what we call adders, that they add, or they implement rollers and shifters and accumulators. And then custom logic is basically the free form, and that's has to however you can define in the digital, in the what's called the VLSI, very large scale integration, or the integrated circuit, where at the nanoscale, the traces of these paths in our fluid model of electricity as about all these gates that employ the effect of the semiconductor to implement what's called the transistor on a particular region of and often a silicon chip. That thus these chips result as these the millions and millions upon billions and billions, or the very large scale integration of what's otherwise an integrated circuit, that in these resources in the analog can be more simply modeled as a diagram as of these working components together, what result these effects in the signals in the overall power of a wave that's kind of as a rushing river compared to all these capillary actions of what you might consider, with the same superfluid model of electricity we've been discussing, the operations of the standard and custom logic. Now, mostly logic in chips is built out in standard logic, and we have languages like VHDL, which is in Verilog, which we use to write where the inputs or pins and the outputs, and then in terms of the logic internally, then all sorts of these things that result for the design and implementation of systems on chip of the electrical sort result that what we're familiar with in that description is usually a simple plate, and electricity flows in the top, and all these gates let it flow through according to conditions on any other given parameters or inputs or the state of the system, that at the end it flows out, and it's all one layer. And so when that has to be a graph of these that's non-crossing, that is acyclic, because it basically it pours in the top and runs out the bottom, and as it flows through these gates, it so indicates variously when the zeros and ones turn on and off. Then there's the idea that at some point in time those are stacked, and at the time the technology allowed that you could stack these layers of the integrated circuit one atop each other, so that you could have, and where otherwise you couldn't have crossing traces because they would interfere with each other, or what's called crosstalk, or chatter sometimes, but crosstalk between the circuits, and which would introduce errors, which is otherwise a deterministic circuit or self-healing of a sort. That then the big columns between them are called vias, and so compared to a trace of the digital chip in the VLSI, the via is like thousands of times bigger, several orders of magnitude bigger. But it's the way that they could stack these chips together and connect them with vias, so that then you could have, in the logic, the way the data flows, that being of a sort not limited or bounded by having to be designed so that it fits on one flat plane of a chip. Then in the modern, then we get up to what's called the freeform 3D IC, where we can implement what are called these fundamental units of the computer logic, like what's called the roller shifter. So you implement the roller and the shifter as about like a barrel shifter in the which is a fundamental small machine in these circuits of billions of them. That then it's possible to design in this freeform 3D IC, three-dimensional integrated circuit, many new possibilities in the design of electrical circuits, which can result that make what would be previously totally impossible things impossible, like cracking all the cryptographic keys or computing in real time, what they call quantum computing or what, these type things. That it's an entire technology that is very remarkable, and it's going to see an incredible amounts of things in terms of what's the theoretical fundamental energy density of matter, in terms of then eventually it will look like a hologram with regards to a what looks like a crystal, and that we approach the maximum limits according to energy density of devices, or computronium, a theoretical material. So he reads on, a great number of other operations in signal processing can be achieved with the help of the above described devices. Kind of like the family of vacuum tubes, which reflect that according to these anodes and cathodes in their configuration and the vacuum within them and the various gratings and the conductors and semiconductors within them, that they reflect all kinds of useful devices in the design of circuits otherwise that have basically what we have the op amp, the oscillator, and some accumulator or counter, will result in our analog devices, and then when that's in the very small and then to the digital devices, how it works out that there's a feet of cats. In particular, if E1 is a Dirac impulse, here in an earlier talk it was mentioned what the Dirac impulse function is as of a flat line with a spike at 0 that goes to infinity, the area underneath which is 1, and that the Dirac impulse is used generally in the methods of convolution in analysis with regards to its displacement to either side, or as Maugin might write it, the offset, that thusly Dirac impulse E1 of tau equals Dirac tau, where this tau is defined in terms of this displacement with respect to time. Then the output signal is given by amplitude st equals v naught integral from negative infinity to infinity of delta t e2 t minus tau d tau equals 1 over v naught e2 of 2t. So he's able to use these methods of convolution to help arrive at how the signal is so resulting that otherwise the means of analysis would be very bereft without this non-standard, not a real function, the Dirac impulse, but it fits perfectly and goes great. So that this produces a compression by a factor 2 of signal E2. That defines what, according to these things, results a factor that then we can consider to the neglection of all other terms of signal E2. If instead we consider a delayed Dirac impulse, E1 tau equals delta tau minus T1, we obtain amplitude equals 1 over V naught E2 2T minus T1. Thus it is it's inverse of V naught, the initial velocity, and then it's a simple quantity of the stimulus, or the excitation, E2, the energy, of 2t minus t1. So then that reflects that in terms of the wave, because it's at an offset, then we can consider that wave when it's delayed. That gets into the notions of periodic motion, that it results that for a given period of, sometimes we call it 2a, but 2 pi, that then it results that this offset helps describe how you can have kind of a row your boat, what results that the chorus or the round is like so. So we obtain this amplitude in terms of this offset, which produces a variable depending on T1 delay of the compressed signal. That it varies on T1, that it cascades and carries over and around, and with regards to echo, 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 or how that would be according to a delay, these things. If we apply E1 to the negative T at the first input, thus it's putting in a contrived, or what results from the implicit providing an explicit that results there's a way to cancel or compose. At the first input, then we obtain the correlation. Correlation is a term that's already kind of reserved by statistical correlation. But this correlation is in terms of any interaction between these effects in this interaction zone. Amplitude of t equals v naught integral from negative infinity to infinity of e1 tau, e2 tau minus 2t d tau, which reflects again that it's linear. Well, it was nonlinear. All right. So then that's reading the rest of section 4.1, or we've made about 3 pages. And, this book only has 150 pages, 160 pages, that over the course of these readings, we haven't skipped over very much, and most of that would be in the appendices about particular materials and thus the large and extended tables of the detail of their materials. That leaves us to where we'll pick up next time with some more reading as after this section 4.3. So then looking at this, yesterday was mentioned the great introduction in geochemistry of solids to atomic theory and the theory of electron orbitals and stoichiometry. And it also helps define, according to the second law of thermodynamics, what is called the calorie, and how we talk about the energy in terms of, as he puts it, forces between atoms, the Schrödinger equation, the representation of overlap of atomic orbitals, according to Pauli and Dirac, who are, besides that Dirac has named from this function from his engineering of physics, that the Pauli principle has that particles are unique and distinct. And then the ionic model, where in solution we talk about materials as of their bonds and being free floating and having a fluid model, or as with respect to their bonds that they have a kinetic and kinematic model. That again, this book at least has a very great self-contained expository introduction to something like the triple point of water with respect to ice and steam or water vapor, and these different types of ice, that is very remarkable. And according to pressure and the Newtonian and non-Newtonian and the fluid and the superfluid and the glasses and the ices, that these states of matter, or phases of matter, are very well explored, and besides just giving us, the tripartite, solid, liquid, gas, that it helps explain what these regimes are and where they change for the triple point of water at boiling, the triple point of water at freezing, and so on. The phase diagram. That this is the great piece there. So I'll put that in a stack. And then yesterday we were talking a bit about the path integrals and quantum processes, and what it basically reflected in terms of the Feynman path integral, and why that's so important in terms of scattering theory and tunneling theory. That, again, the Dirac delta has a very significant and central role with regards to, for example, just reading happenstance, from Soisson, very often a function has no periodicity. Another way of expressing this is to say that the interval of periodicity is infinite, and this is represented mathematically by taking the limit L goes to infinity in the previous formula, which is the periodic form for the Dirac delta. A modeling of it by being a limit of a family of standard real functions being not a real function. In this limit, the sum in 1.14, which is a Dirac delta representation in terms of a Fourier series, which has its merits and otherwise has places where it's not what to have, may be converted into an integral with the result that delta x minus y, the displacement of x minus y by y, equals 1 over 2 pi, where 1 over 2 pi is simply the reciprocal, or the of the 2 pi, the representation of the parameter of the terms, the periodicity of negative integral of negative infinity to infinity of dk times e to the I imaginary times k quantity x minus y. Thus, that is parameters in terms of a differential function, or is about that the exponential function is its own antiderivative, and that thus that these differential functions admit a very particular forms of systems of solutions according to their initial values and their regions of x minus y. That this delta is so read like so, thus that in other questions about its placement in and out of convolution, that the Dirac delta has some context necessary and relevant its application to preserve that it's well behaved formally. And not all mathematicians or scientists or physicists or chemists are always formally conscientious, because sometimes it's the empirical or what works, their working theory. But formal rigor for the conscientious mathematician is required. And our derivations all together must all fit together, whereas they be formally reliable, vis-a-vis usually reliable. In the what's then would be called the deterministic and the idempotent, that given the same conditions, there's the same result. And so he begins in these preliminaries of about why we use the Fourier series and transform, because the Fourier has the series in the wavelength and the series in time, and about the transform, the separation of the components to reflect the orthogonal components to make the Fourier transform. He starts talking about eigenvalue problems, and eigenvalue is about the Hermitian operator, and as about the existence of the adjoint and the self-adjoint. That thus the product spaces are so defined in terms of these tensorial quantities, why it works out that there are solutions that can be made up, derived, that these are usual and same mathematical preliminaries for Maugin, if 30 or 40 years later, basically that they reflect the same platform, if not necessarily on our same foundation, where a foundation is all the utterly fundamental elements, whereas a platform is given any set of fundamental theorems about the objects of discourse, that you can consider those as alone in a context, vis-a-vis having to explain the entire kit and caboodle, which is a phrase representing the entirety. And then he talks about functionals in our real valued functional theory, because when we start talking about real valued functions and not real functions, sometimes we talk about degenerate ideas of as defined before, about like the functional, or we talk about things that have to do with operator calculus. That operator calculus and operator theory is basically the idea that these operations define and describe for these objects of what would, for example, be arithmetic, or these vectorial quantities or tensorial quantities, that the operations exist, and that the operations are either open or closed with respect to that the operation carried out on an objects of the type, left-hand side and right-hand side, for objects of the type alone, the unary, and left-hand side, right-hand side, the binary, that these functions result that the inputs and outputs of the function are the same type. So that then we talk about the operator calculus is basically the existence of these things, and then that with regards to something like algebra, that our usual abstract algebra is the existence of these things, and then how we can treat symbolically the behavior of the objects under these things according to what's all collected as after being defined, what can so be derived, their behavior, given a particular contrivance or the setting in a space. Well, all right, that was some reading for today, and it's filled about 3/4 of the hour. And then, let's see here. I want to get to reading some of this from the continuum at some point. Herman Weyl's continuum. Because the continuous and discrete is really almost the fundamental study of numbers. He says, in the note to the Dover edition, the translators also benefited from the advice and encouragement of many outstanding scholars, especially John Corcoran and Ignacio Angelelli. So John Corcoran was referred to in an earlier talk as about, from reading Nozick or the Axiomless Natural Deduction, about how we want to arrive at what is continuous and what is discrete as of by first principles. So I won't so much get into reading yet so much about Weyl's description of the calculus or the continuous, but first I'd have to mention Carl Boyer's the conception of the integral calculus and its conceptual development. He wrote a history about Newton and Leibniz and what was before and what was after about the continuum of what we call real numbers. And also we point to Thomas Hardy, if I have that correct. Hardy wrote a textbook in the early 20th century that equates the points on the real number line with the real numbers as of these algebras of real numbers. And these other settings where it's axiomatic, thus elementary, thus fundamental, what are our definitions, ... that so follow the result, we have models of real numbers, and that any of these objects, thus so modeling the arithmetic of real numbers, thus so fulfill any algebra, what's based upon those, just as this algebraization, or making algebraic this thing, has that any arithmetization of those by resulting that its operations are modeled by the operations of arithmetic on numbers, so results that these are all the sorts of things that go into the abstract objects of mathematics, which include the continuous or a continuum, let's call it 0, 1, or the unit line segment, or the unit, or a whole, a monist whole and complete thing, and the discrete, which is a point on that line. For these points in a line, that there's a point on a line, and that our reference to its measurement is as so subjective as about the objective of the existence of this thing, that the results that then we can talk about a framework for what's called the field of rationals on what is this continuum of points in a line, a clock arithmetic, or an Aristotle's continuum. Thus that we can talk about an Aristotle's continuum of points 0, 1, contiguous, and yes, non-standard, because standard real points are not contiguous, because between any two standard points, you can take their average and it's different than them and between them. But the idea is, and so they're not contiguous with no intervening neighbors, that a notion of Aristotle's continuum and a notion of Dedekind's continuum, or Cauchy-Weierstrass's, really, and for the theorems of Cauchy-Weierstrass that are definitive in how we establish our fundamental theorems of real analysis. Then there's, say, a Nyquist or Shannon continuum of a signal analysis, that the rationals are so dense that twice them is continuous. That these are the kinds of ideas that complement what we have to deal with in terms of, as we've been talking about, conservation laws and physics, and how it's all defined in terms of these effects interfaces, that it also admits a definition about being the continuous. Because, for example, when we talk about space-time and the objects occupying numbers in the field number formalism, that in quantum particles everything's a point, well, everything's a wave, and everything is part on the same continuous manifold. And then that in terms of what results, something is effectively infinite and effectively continuous, where the grain is smooth, or that there's the atomicity, that it's atomic, and also the surface. That these are the kinds of things that really get into why we have, for the foundations of mathematics, first, that the usual foundation satisfies first all finite combinatorics and all the things that we can build up from simple and linear and classical first principles, and then about how it needs be that the real, true, fundamental theory has to explain why there is a continuum and what it is. And it's kind of remarkable that all in prehistory, and where we look back at history as like 2,000 years ago, 0 AD, Anno Domini. Before that, it was called before Christ, or before the Common Era. And 2,000 years before that was the advent of the Egyptians. And 2,000 years before that was kind of the fall of, or when the Upanishads and the Indics in Greater India at the time, 4,000 BC, there was a great fall and the great flood and this kind of thing. And then there's about 6,000 BCE, and then there's some ideas about that. There's another catastrophe, or what happens every couple thousand years, or doesn't. And then with regards to this time, this symbol of mathematics was this spiral space-filling curve that is basically reflects the notion of a continuum, because it's contiguous points as grow into a ball of matter while drawing a line. So when we look back at all ancient antiquity, where since there are no written records, and the only thing that really survives in terms of an oral tradition was the Upanishads or Vedas of the Indics, from which most Western languages are in part descended, though there are different spots of culture as of various places throughout the world in history and since before, that then when we get talking about the foundations of mathematics and physics, it so arises from where the continuum is a primitive object. It's primary, it's elementary and fundamental. And this is a necessary thing for us to have a mathematics, so that then we can equip a physics, that our models of mathematics have that internalized and functional and non-contradictory, and towards being consistent and complete, that after it's constant, it can be concrete. That these are the desiderata, what we need, of such a theory, that it results then for the notions of unified theories, that it's a thing. So, for that being, a description from Maugin of today about this particular experimental apparatus and functional component or device that has, according to these mathematical models, these physical models, their interpretation, according to what thus results, that it's so defined that the constraints of the device can so be contrived that it arrives at function given simply the properties of work that restitution and oscillation and dissipation and attenuation naturally do in entropy, or as accordance to the gradient of things. Then with regards to that, it's all one picture. This mathematics is enduring, and so it's certainly something to find a common thread, that it is among reasons why the discrete and continuous is such a compelling object of study, and central, and as well that is the context, that these type things help advise us of what in our brief time that in our utilitarian demands upon us, that is the least toolkit you need to know to have an understanding of these things. And so that's been my study for quite a while. All right, then. It's been the study always. Well, then, good afternoon. Let's see here. 5507. Good day.